Okay, now before we just move on to just go to the final step that we have in mind, which is going to be finding a method in order to compare two models which they have been fitted by a Bayesian analysis, then the thing that we just want to do is that at this stage we want to essentially talk about and finish the thing that we just started from the previous tutorial about the important sampling method that we talked about that on the previous session. But however, in order to continue with this session today, we just have to just install a package, which the package comes as the name of the loop, which stands for leave one out. And that's the package we're just going to talk about, the intuition that how the leave one out cross-validation method is going to be used in order to evaluate and compare two or many other methods at the same time. But however, before we just get to that point, I just want to talk about the one basic thing, and that is going to be the fact that if you remember, for example, from the importance sampling weights that we had, when we just plotted the density, if you remember from the previous tutorials, we normally get a density like that. And for example, if you remember also from, we just had to just run a command, which it was, I should say, it was called the weight plot from the edges. And if you remember, for using that thing, we talked about the objects that we had. It was WX. And for this one, you remember when we just executed that command and that code, we just got 4 plots. That 3 of them were essential for as a kind of a diagnosis and a diagnostic method in order to see the importance weights that we have had, if they are going to be reliable. And as you can see, particularly the variance section, which showed that the variance of our proposal, I should say the distribution, is a finite variance, and it's essential. As you can see, it gets some kind of stability, and it looks that there is some kind of a convergence to a value, and that was essential that we talked about that before. And exactly on the previous tutorials, I recommend you, if you just started from this tutorial, just go back, check the one which you had before. And these plots, it was very crucial that we talked about that, I should say, on the previous session. And also you remember that we just talked, we can also plot the density of, I should say, these WX, these weights, and you will see that we somehow get something like that. However, the plan that we have to just do right now is that we you see that there are some points, I should say, that we have, there are some weights that they are significant and they are tolling, I should say, the whole distributions towards themselves if you have a density of these ones. The thing that we just want to do, I just want to also come here to show you a kind of a distribution. And that distribution, which I have here right now here, as you can see, this is going to be a Pareto distribution, which I have the Pareto distribution, which you can see that from different values of, I should say, from the parameter shapes, for example, for alpha equal to 1, for alpha equal to 2, for alpha equal to 3, and alpha when it goes so incredibly large and goes to infinity, we will see that the shape of, I should say, the Pareto distribution, it changes. For example, the red one, it corresponds to the shape parameter of the tree. Or let's say, for example, look at the blue one. The blue one corresponds to the shape parameter, which corresponds to shape parameter to 2. And if you look at the green one, it corresponds to the shape parameter, which is going to be, I should say, 1. Then you will see that these, that's why we call them a kind of a shape parameter, because somehow in a way they dictate, they control the shape of this distribution with respect to the value that you choose for these parameters. And you see that you have a restriction to choose a parameter which is going to be a positive integer. Then as a result, that's how you see that these shapes, we have just different shapes for different parameters of the value that we have. You can have any positive value in terms of the parameters that the shape parameters that you have for, I should say, for the parameter shape. And if you go back again to the R, to the plots that we have as a density of the weights that we have, just go to the R, and if you see that, for example, this part, I should say, of the plot, it seems that we can essentially, if I go back again to this parity distribution, you see that it somehow resembles, if I just want to zoom in back to this plot which I have here, you see that as the higher indexes, you see that this part of the plot, which it resembles like a parity distribution, but the thing is that we do not know what is a parameter of that distribution, that we can just have this distribution, parity distribution at the extremity of our distribution of our importance sampling weights. And that's going to be the thing that we are going to talk about it right now. We are looking for a method to fit a parity distribution at this part of the importance sampling weights, and by doing that method, the thing that we are going to look into to make an inference about the optimal parameter, shape parameter of the parity distribution, that it's the best fit for this one. Then from there, we have an object. We can just move on and infer some methods for when it comes to the model diagnostics in the Bayesian context, and also model comparisons between two different methods that which they have been fitted, but in Bayesian methodology. Then that's going to be the method that we are just going to do right now. However, in order to do that, as I said, we are in need of two packages. There's one package essentially, and effectively one package, which is going to be the LOO, which stands for leave one out in cross validation. If you install that package, you expect that, as you know, you have to just go to the package tab. You just scroll down all the way, go to the section L, and you see that the LOO, which is an efficient leave one out cross validation, and Watanabe information, the criteria for Bayesian methods. We do not just going to talk about the weight. The thing that we're just going to work is going to be simply with the LOO, because it provides some diagnostics method when you just do some cross-validation there. However, now, I'm just going to, in order to use this method, the thing which I'm just going to do, I'm just going to go back again to our simplest model that we had. If you remember in the past, in tutorials before, we worked with the data sets women, and we just defined a model A, which the model A was a Bayesian regression method on the woman data sets, which was an internal data sets in the R, and we used this Bayesian regression, linear regression, in order to have a prediction and model these women's height with respect to the weight which they have. And if I just want to just click and execute this code, you see that the model which we created before, it's essentially, it used a Gaussian method in order to just predict the women's height from their women's weight. And we had 15 observations, or 15 women in our, I should say, experiments, which they had two predictors. The predictors, one of them was the height, the other one was the weight. And you saw that by doing that method, we were able to probabilistically find an inference for the coefficients of our method, which was one, the slope for the weight, which it seems that it's going to be 0.3, and also one coefficient as a kind of an intercept, which it was 25.7, and essentially that was the thing that we did in the past. And also, if you remember, in those tutorials we talked about in the past, we talked about that it was a kind of a probabilistic approach, because we find the probability that, what is the probability that we find, for example, these slopes, these inferences to fall into a certain range, that we talked about that, and we call them credible intervals, and we saw how we can just, I should say, use some methods in order to graphically visualize these credible intervals, which they are some sort of the uncertainty which are going to be attached to the inferences that we have made in our linear model then. However, the thing that we just want to do now, I'm just going to use the model which I created in the past in order to just see what is going to be my smoothed weight, because the reason that I just tried to fit the parity distributions into, if you remember, for example, into the distribution of my importance sampling weights, was that to smooth these, I should say, those weights that there are, just give a kind of a odd shapes in my sampling weights distribution. Then in order to do that and just smooth them, I'm just gonna go ahead, start with the model which I had. For example, this one which I had here, this plot, it doesn't go back to the thing which we did. We are just going to go back to the packages, which this is in the loop, the functions within the loop. And for the model which we had, it's going to just generate, I should say, the proposal distributions. And from there, everything is going to be done automatically as a function which is going to be called PSIS, which stands for Pareto Smoothed Importance Sampling. Then we do not need to just every step by step. We do not need to just go, for example, find the proposal distributions, do the diagnostics, then fit the parity distributions to the, I should say, the distribution of the sampling weights, and do the diagnostics from that stage, and everything is going to be done and ready just in a couple of, I should say, seconds, and as you will going to see that. Okay, now, the thing that we just want to do, we just start from the model that we had, from the woman's height and weight. And now, in order to just go ahead, I'm just going to use a package from the R-stand arm. I'm just going to go ahead with the pointwise logical, I should say, log likelihoods that I had before. We never used that package before, and I'm just going to use it right now, because in order to use the PSIS functions, I need the creative functions to create an object which is the result from, I should say, from pointwise log likelihood, which is essentially the prediction, I should say, from each simple observations from your data sets. Okay, in order to do that, I'm just going to need an object, which is going to be the objects which I had, is essentially the same thing which I had. It's going to be my model A. It's essentially any Bayesian regression model that you have prepared on your research then. You can just start to just put the model which you have from your research then. It's gonna, for me, for the sake of the demonstration, it was the model which we probabilistically created, which predicts the woman's height from their weights. And now also the other thing which I do need is gonna be the terms. It's gonna be the data which I use that in order to make that model, which, if you remember, was a woman data sets. Now, it seems that we should have everything prepared. I'm just going to press F1 to see that if we have everything which is needed for my purpose. You see that for the log likelihood, we just need the one which is going to be the R-stand arm, and as it says that, it's just for the MCMC methods. And now let's see, the things that we have is going to be ready, and before I just move on, I'm just going to execute the code by pressing Ctrl-Enter, and you see that there are some weights that have been all created there. And now, the thing that we just want to do is this. I'm just going to store this thing into one single object before I just move on to use that object for my future analysis. I'm just going to create a name. I'm just going to create it as the like woman A. I just create that name in a way that it always rings a bell for me when I see that object's name. It reminds me that's the kind of a log likelihood for the woman A, which is a Bayesian method to predict the woman's heights from their weight. Okay, before we just move on, I'm just going to go ahead and I'm just going to do some kind of simple things to do with this method. I'm just going to check the dimension of the woman likelihood, because there is something that I need to just explain that to you about that. You will see that when you check the dimension of this object which you created, but also before we just do that, it's good also to check the class. You see that when you check the class, it's going to be a matrix or array, which essentially shows that the matrix which you have, it's 4,000 rows and 15 dimensions. Which right now at this stage, this 15 and this 4,000, it should remind you of one thing. This 15, which is going to be the number of the columns or features in our objects which we have, it's essentially every single observation that you have in your experiments. In our experiments, the observations which we had, it was the unit of observation. It was the women. We had 15 women. Then as a result, I have 15 features, or I have 15, I should say, observation in this model. And that's why the dimensions of this object which you create as a pointwise likelihood is going to be 15. This is exactly a correspondence between your experiments, I should say, number of the observation, and the columns which you have as a result of pointwise likelihood. And also, you have 4,000 rows, which essentially, it reminds you of one simple fact. That if you remember, in our Bayesian analysis that we did, we had 4, I should say, chains. That each chain, in parallel, they draw 1,000, I should say, 1,000 times on 1,000 trials, they draw samples from the posterior, I should say, density which you had. And then as a result, for each rows, you had, if you remember, from the posterior predict functions that we had in the past, for each rows, you had one type of a predictions for the woman's height. In some of the examples that we had, so in some of them, we just tried the number of the repetitions, the NREPS arguments in the posterior predict, sometimes you go to the 600. Then now you see that in the maximum one which we had as a default in our codes, it was 1,000 trials, 1,000 times we had, I should say, the sampling and those from the posterior density in our parameter space as a kind of a method that it just predicted for each trial the heights of those women. Then as a result, we expect that because we had 4 chains which in parallel they were just picking up, I should say, drawing from the, I should say, the posterior density, then we have 4,000 rows, 4,000 trials from our posterior formations, or from the, I should say, parameter space in our data sets. And that's the reason you see the dimension of the object which we have created is going to be somehow something like this. And now that we are at this stage, now I think that's going to be a good point not to just make these tutorials to go too long. I'm just going to stop at this point. When you come back at the next tutorial, we are just going to create another object, which is going to be essentially the effective number of, I should say, samples, the total number of the rows which you have, in order to create all the things that we need, in order to make our first functions as a fitting for Pareto smoothed importance sampling depth. Then I hope that at this tutorial, you were able to get to know that how we can just create a pointwise likelihood functions from the Bayesian model which you have created before that. I just come back in the next tutorials to continue our session.